Alrighty, so we actually have 6 trigonometric functions. In geometry, you tend to only use 3 of them. So when you were working on right triangle trig, you probably used sine, cosine, and tangent. And those were the 3 that were in SOHCAHTOA, right? You probably didn't use the other 3 that we're going to introduce for today. So again, remember, in geometry, you were looking at right triangles. You were looking at for my angle, is this based on the measurement I want? Is it based on the hypotenuse, the opposite side, the adjacent side? And you used SOHCAHTOA to talk about them, right? So for sine, and spell check didn't like just the abbreviation there, but for sine, you talked about this as the sine of this angle is the opposite side over the hypotenuse. That's the SO in SOHCAHTOA. So you talked about this as being the opposite over the hypotenuse. Cosine was the ka, the adjacent over the hypotenuse. And tangent, the toa, was the opposite over the adjacent. Okay. And that was basically the trig that you did in geometry, right? You didn't do much more than this. Sometimes you did inverse sine or inverse cosine if you didn't know the angle, but you knew the sides. But beyond that, you use sine, cosine, and tangent. You use SOHCAHTOA. Maybe you did some converting from degrees to radians, but that was the trig that you did in geometry. In Algebra 2, we will also use these properties to an extent, but we'll also say that tangent we can define as sine over cosine. So sine of my angle over cosine of my angle is another way that we can define tangent. If I think about taking the oa and the ka, right, or the soa and so and the ka part of SOHCAHTOA, I should say, and we let sine be opposite over hypotenuse and we let cosine be adjacent over hypotenuse, we would come up with this same thing. If I'm dividing fractions, that would be multiplying by the reciprocal. My hypotenuses would reduce out, and I'm left with that O over A, the opposite over the adjacent. So I get the same thing, but in our trig material for Algebra 2, defining tangent as sine over cosine is going to be a little more helpful for a lot of our problems. So that's half of our trig functions, the half that you are familiar with. We also have what are sometimes called the inverse trig functions because they are the inverse here, okay? And we've got cosecant, which is going to be the inverse of sine. Secant, which is the inverse of cosine. And cotangent, which is the inverse of tangent. So essentially, I am going to take the reciprocal of each of these, or reciprocal, I should say, reciprocal identities. So this would be, if I were looking at a right triangle, hypotenuse over opposite, hypotenuse over adjacent, and adjacent over opposite. Okay, reciprocal. Reciprocal is the word we want there. So these are the other 3 that we get, but they're based on the 3 that you already know. So we're going to do just a couple of problems that are kind of more in that geometry territory of here's my right triangle, here are the side lengths. And then we're going to see how this kind of transitions to that circle and the radian degree measure that we were talking about. So in the figure below, we want to find sine of alpha. Okay, so sine of alpha, you guys could do this last year or the year before, whenever you had geometry. So you were looking at the opposite side over the hypotenuse. This would just be 8 over 17. This is the kind of stuff you guys have done before. I've just added in some of our new trig functions. So secant is the reciprocal of cosine. Cosine would be adjacent over hypotenuse. So we want hypotenuse over adjacent. We want the reciprocal of that. So that would be 17 over 15. Tangent, you've seen before, opposite over adjacent. Cotangent is the reciprocal of that. Remember, cotangent is the reciprocal of tangent. So it would be the reciprocal of our tangent value here. So when we talk about angles, they're not going to be on a triangle set apart all by itself. They are going to be angles in standard position on the coordinate plane, like we talked about last time. Okay, so I'm going to be looking at something where this angle is right at the vertex. The initial side is along the x-axis. My terminal side is somewhere here. And it's a pretty good bet that my angle is going to be one of those that we talked about just a minute ago. Okay, just a bit ago. Those most commonly used sort of radian measures. Okay, it's a pretty good bet that whatever I use for here is going to be one of those. The other consideration that we make, or the other sort of stipulation that we put on a lot of things, is instead of having to think about all different kinds of triangles, and you guys talked about special right triangles probably in geometry, 3, 4, 5 triangles, 8, 15, 17 triangles, those different families of triangles. What we'll tend to talk about are triangles where the radius has a unit of 1. Okay, we're going to look at triangles most commonly where the radius is a unit of 1. This is what we call the unit circle. Okay, the unit circle is centered at the origin. Any triangle that we're looking at is going to be inside the unit circle, and its radius, its hypotenuse, I should say, will be a radius, and the radius of the unit circle is a 1 unit. That's why it's called the unit circle, because its radius is 1 unit. If I were to think about the equation of this circle, you guys do equations of circles in geometry? Probably like 100 years ago, but you did equations of circles in geometry. The equation of this circle would be x squared plus y squared equals 1, because it's at the origin, the center is at the origin, and the radius is 1. So then what we're going to be looking at for our sine, cosine, tangent, secant, cosecant values are not the ratio, because the hypotenuse is 1. So that means for a lot of this, what we're going to be looking at, if the hypotenuse is 1 and I ask you for the sine, I'm just asking you what's the length of that opposite side, right? If it's over 1, it's just that side. If I ask you for the cosine, I'm really just asking you what's the length of the adjacent side, because it would be that over 1. So what we get at are really what's the coordinate of that sort of radius, the end of that radius on the unit circle. The cosine value would correspond, right, with that adjacent side. Well, that's how far on the x that we went, right? Since cosine of that angle is the adjacent over the hypotenuse, in this case, x over 1, that's just x. That's just my x coordinate for the point on at the end of my radius. For sine, same idea. Sine of theta is opposite over hypotenuse. Well, the opposite is y. How tall is that side? It's y units tall. And the hypotenuse is 1. Well, that's just y. That's just the y coordinate of whatever this point is. Tangent, then, we know we can describe as sine over cosine. This will still be a ratio of y over x. Since sine is our y value, cosine is our x value, it would be the ratio of y over x, the y coordinate over the x coordinate. Cosecant is the reciprocal of sine. So we would be looking at the reciprocal of the y coordinate. Secant is the reciprocal of cosine. So we would be looking at the reciprocal of the x coordinate. And cotangent is the reciprocal of tangent. So this would be cosine over sine, which would be x over y. So we're going to work through a few examples today of tying in those angles and radian measure that we just talked about, okay, with what would be the coordinate at the end of the radius on the unit circle. Now, some of our angles lie on an axis. Those points are easy. It's a unit circle, right? So we're only ever going out as far as 1 on any axis. That's the biggest number we'll ever get is 1 when I talk about an individual coordinate, right? So if I'm at 0 or at 2 pi, that would be right here. That's the point 1 comma 0. I know it's 1 comma 0 because it's the unit circle. The radius is 1. If I'm up at pi over 2, that would be 0 for the x and 1 for the y. At pi, we would be at negative 1 comma 0. At 3 pi over 2, we're down here, right? 3 pi over 2 would be here. That would be 0 comma negative 1. So if I asked you, what's sine of pi over 2? Okay, remember sine is the y, cosine is the x. So what's the y value at pi over 2? At pi over 2, this is a y value of 1. So sine of pi over 2 is 1. What's sine of pi? Sine of pi. Pi is halfway around the circle. Sine y value. The y value at this point is 0. We are on the x-axis, so the y value is 0. Sine of pi is 0. What's cosine of pi over 2? So cosine, or pi over 2, I should say, is up on the y-axis, right? A quarter of the way around our circle. We're up on the y-axis. Cosine is the x value. When I'm on the y-axis, the x value is 0. So cosine of pi over 2 is 0. Cosine of pi means we're here, right? Halfway around the circle. Cosine at this point would be negative 1 since my x coordinate is negative 1. If I asked you for tangent of pi over 2, that's where I've got to look at the ratio of sine to cosine. So remember, tangent is sine over cosine. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. What can we say about tangent of pi over 2? It's undefined. When I start looking at some of those ratios or some of our reciprocal identities, we might get some stuff that's undefined, especially on our axes. Tangent of pi. So that would be the sine of pi over the cosine of pi. What would I get here? 0. Questions for me so far? Okay. On the next page, we're going to look in a little bit different way at some of those most common angles that we talked about earlier. Okay, so pi over 6, pi over 3, pi over 4. Okay, we're going to think about those instead of having you just try to memorize like the points on the unit circle, right? This was the page from our packet earlier. Instead of just telling you, well, just memorize all these points. Okay. What I want you guys to be able to do is reason through why these points are what they are. Why is this root 3 over 2, comma, a half? Why is it root 2 over 2, comma, root 2 over 2? Why? Why are those the values that they are? Okay. Special right triangles can help us out a lot here. So one more thing that we're going to borrow from your trig time in geometry were those special right triangles. The big ones that you guys probably talked about were 45, 45, 90 triangles. There was a special pattern there. And 30, 60, 90 triangles. There was a special pattern there as well. I have those triangles here for us. Notice these two are the same. It's just sort of rotate. It's like reflected, right? Instead of the 30-degree angle being up there, it's down here. These are the same triangle, right? 2x on the hypotenuse, x on the short side, x root 3 on the long side. Okay, same triangle, just different orientation. So we can talk about those different angle measures. 45 degrees is pi over 4. 60 degrees is pi over 3. 30 degrees is pi over 6. Okay. That's why we use these triangles in particular, because they match up with those most common radian measures that we're going to see. Now, we know our hypotenuse on the unit circle is 1. So I know that this guy is 1 and this guy is 1. And this is the same guy, but he's also 1. So if I talk about these angles in standard position, right, this would be my x-axis. This would be my y-axis, right? Angle at the origin. There's our angle. Same deal here. Angle at the origin, initial side along the x-axis. There's my angle. And then same deal here. The angle that we care about, centered at the origin, initial side along the x-axis. And there's my rotation to my terminal side. So for my unit circle, if I've got angle measures of pi over 4, pi over 3, or pi over 6, we know, again, on the unit circle, the hypotenuse is 1. That allows us to figure out what these remaining sides are going to be. So if I've got my unit circle, let's say here, and my angle of pi over 4, I can drop a side down so that I can actually see the whole triangle, right? We just worried about drawing where that terminal side was going to be, but drop the side down so you've got a triangle, right? We know the hypotenuse is 1 because we're on the unit circle, right? Hypotenuse is 1 on the unit circle because the hypotenuse is your radius. I want to know what's that point. To be able to talk about sine and cosine, we're looking at what's this side and what's this side. Well, this side is going to be the y coordinate, right? The y value. This side is going to be the x value, the x coordinate for that point. Since we know stuff about 45, 45, 90 triangles, I can figure this out, okay? I know that root 2x is equal to 1. So if I want to know what x is to figure out my other sides, right? My x and my y, we just solve for x. Divide both sides by root 2. In your geometry class, you may or may not have talked about rationalizing denominators. I know if you go on to take calculus on the AP exam, they don't care if you rationalize denominators. However, when we talk about trig, almost always our values do have a rationalized denominator. To rationalize a denominator means we do not want a root left in the bottom of a fraction. So to get this root out of the bottom of our fraction, we multiply by that root on top and bottom. This is okay to do because I am essentially multiplying by 1, right? A number divided by itself is the same as 1. But when I do this, we would have root 2 on the top, and then root 2 times root 2, that would be the square root of 2 squared. So on the bottom now I have a rational number, just 2. So that means that this side, right, x would be root 2 over 2. And in a 45, 45, 90, the sides are the same. So this side is also root 2 over 2. So down here, where my hypotenuse is 1, this side of our triangle would be root 2 over 2. This side of our triangle is also root 2 over 2. So this coordinate would be the x amount, root 2 over 2, comma, the y amount, also root 2 over 2. So when I look at my unit circle that was printed on my notes page, and I look at an angle of pi over 4, there's a reason why I get the coordinates root 2 over 2, comma, root 2 over 2. It comes from our special right triangles. And I can do the same thing with our 30, 60, 90 triangles for an orientation of pi over 3 and pi over 6. Pi over 3, right, where the 60 is our angle that we're interested in, would be here-ish. Okay. We're looking at this angle. Pi over 3. I can create a triangle out of this, a little right triangle. My hypotenuse is 1. For my special right triangle, okay, the hypotenuse is 2x. So let's solve for x because I need it for these other parts. So 1 equals 2x, divide both sides by 2, and we get x to be a half. So that means our short side is a half. Our long side is root 3 times a half, or root 3 over 2. So the coordinates for that point would be the x amount, which is a half, comma, the y amount, which I'm going to run out of space here, is root 3 over 2. Same thing that we see here for pi over 3, a half, comma, root 3 over 2. It's from our special right triangles. For the last one here, where our angle is pi over 6, that would be about here. Here's our angle of pi over 6. Hypotenuse is 1 because the radius is 1. We can drop down a side there to see our triangle. And then this is the same triangle we just did here. The short side is a half. The longer side, the longer leg, is root 3 over 2. So the coordinates for that point are x comma y. So the x amount is root 3 over 2, and the y amount is 1/2. If you ever forget these measures, we're going to work with them enough in this unit that some of them you'll just start to have memorized. When we come back to unit circle problems later on, and you don't have this unit circle memorized anymore, I want you to remember that there is always a way to figure out what those values are. For some of you next year or in 2 years, when you're in calculus and your teacher is making you tell them about the sine of pi over 3, right? And you don't have it memorized anymore because it's been 2 years, there's still a way to be able to figure that out, okay? So from our sketches above, if I want the sine of pi over 4, right? Here's pi over 4, sine is the y coordinate, root 2 over 2. If I want the cosine of pi over 3, cosine is the x, that's a half. If I want the tangent of pi over 6, here's pi over 6. Tangent is going to be sine over cosine. My sine, the y, is a half over cosine. That's root 3 over 2. I can set up that ratio using those coordinates. For this guy, I would have to flip and multiply. I would get 1 over root 3. So I've got to rationalize again. But we would get root 3 over On the bottom, that'd be root 3 squared, which is just 3. Secant of pi over 3, that would be 1 over cosine of pi over 3. The cosine of pi over 3 is 1/2, so just the reciprocal of that would be 2 over 1, or just 2. We will stop there for today. Just a couple more things that we'll talk about next time. I would like you tonight for homework to work on the Khan Academy assignment that is posted for you.